Thank you very much for the introduction, Raquel. So I will present two studies today and the corresponding methods, and both tie into the things that we've heard before. So I thought I will give first a very brief overview of basically the some related topics, things you need to know to understand the rest of the talks. So, and that's the suggested role that our brain rhythms play when we listen to someone speak. Then I will talk about the prevalence of intrinsic brain rhythms and the associated method of analyzing spectral fingerprints. And then I will talk about the role of neural tracking for speech comprehension and introduce another method that allows us to measure how well our brain can follow some external stimulus. So we've heard about this from Christian and from Noor, and I will introduce mutual information, which makes it particularly easy to analyze naturalistic stimuli. Okay, so first just a brief overview of what we think might currently be happening when we listen to someone talk. I do have a slide that introduces brain rhythms, but I think we can skip this, because I think people know what brain rhythms are, right? Okay, so I just skip all of this. You've heard about this before. So we have different time scales of rhythms in the brain, but at the same time we also have different time scales in speech. And there's a stimuli that I usually play, which we didn't get to work here, but basically you hear a pleasant male voice saying, last Sunday night, David examined 5 beautiful paintings. And this is just the second part of that sentence depicted with its waveform. And in this little snippet of speech, we already have lots of different time scales. So on the one hand, we have phrases, and there are 2 in this part. Then the phrases consist of words, the words consist of syllables, and the syllables consist of phonemes. And these are all hierarchically organized, and it's a little bit similar to brain rhythms, really, who we also think are probably hierarchically organized. And well, the current idea, what happens in the brain when we listen to speech, is that our brain activity aligns to these different timescales in the speech signal. And that is mainly the auditory cortex, but also other areas as well, that basically follow the slow fluctuations in the speech signal and align their activity at all of these different timescales. So we have what we call cortical speech tracking at different timescales. Some people call it cortical entrainment. And this is thought to lead to a representation of speech in the brain. The suggested purpose of these processes is that it segments the ongoing continuous speech stream into its different linguistic units. For example, if you think about the word scale, if you don't know where a word ends or begins, then you have no way of finding out what the word means. So this segmentation into words, but also into syllables, is really, really important for us to understand speech. So that's the whole idea, that this tracking is important and allows us to understand speech. And it's also thought to be a predictive process, so not just following everything that we hear, but the idea is that actually the brain actively tries to predict what's going to happen when the next word will start, so that it can optimize the timing to analyze this kind of word and to understand the words. So this is the idea, and what I've just described is basically entrainment. And what entrainment would mean is actually that we have intrinsic brain rhythms that are always there, so that don't just pop up when we listen to speech, but that are always there. And these align to these different time scales in speech. And to illustrate this a bit further, that would mean that to be able to track different phrases in the speech signal, we would have to have a low delta rhythm that basically resets whenever a phrase starts, and then when the next phrase starts, it resets again and basically tracks and encompasses these different phrases. Then we'd need another delta rhythm that is able to track the occurrence of words. A theta rhythm that it would be able to track the occurrence of syllables. And another one, beta gamma. People are not too sure which one. And that should be able to track the occurrence of phonemes in the speech. So in theory, we would need to have all of these different brain rhythms in our auditory cortex already, that then, and these can then track these different timescales. But this is very, very much debated, especially in the case of speech, because speech is not rhythmic. If you think, for example, about words can be extremely short. Like if you think about the English a, that's basically as long as a phoneme. It's just one phoneme. And then there can be really, really long words. The idea that there's a single oscillator in the brain that can adjust its frequency to all of these different ranges and that can be that flexible doesn't really make sense. So it's quite tricky. The only case where it might make sense is actually at the syllable rate, because syllables are relatively rhythmic. At least they're rhythmic enough to lead to like a peak in the modulation spectrum or in the power spectrum. So if you analyze speech, you see a peak at between 4 and 5 hertz usually, and that matches our syllable rate. So I'm very, very skeptical with this whole entrainment idea when it comes to speech, but the only case where it might actually be happening, I think, might be theta, and there's some behavioral evidence that this might be the case. So then an alternative, or not even alternative, but another mechanism that very, very likely plays a role also in speech processing, just like in other like flickering paradigms or stimuli, are evoked responses. So here the idea is just that whenever there's a landmark in the speech, for example, like an acoustic landmark like word onsets or syllable onsets, then we just see an evoked response in the brain. So the auditory cortex just does what it does and analyzes sounds or represents sounds. And because there are many of these landmarks in speech, we see these successive evoked responses, and we see what we see in the EEG signal. And when we look at the EEG and look at speech tracking, we can't really disentangle between these two mechanisms. Or it's very, very difficult. Some people have tried, but it's quite difficult. So basically, we still don't know whether entrainment plays a role in speech processing or not. But there's one thing that leads me over to the first study that I would like to present, and the first method, which is that we can look into intrinsic brain rhythms. So we can look, for example, at the auditory cortex and see which brain rhythms are there when there's no input, just like intrinsically or like without any task or spontaneously. So this is the next part. So we wanted to see what is the prevalence of brain rhythms. And we did this, we analyzed MEG resting state data. So MEG, probably also everyone knows this here, big brother of EEG. And we had a data set where participants were just resting for a few minutes without having any task. And then we analyzed regional spectral fingerprints. And I will go into the method a bit more in a second. So we looked at the whole brain, but I'm just going to show you here the results for the auditory cortex. So this is the primary auditory cortex, left and right, so Heschel's gyrus, basically. And what you see here is at the x-axis the frequency in hertz, and then on the y-axis the power. And whenever you see a peak here, that basically means that there's an oscillation in this area at this frequency. And I've labeled them with the corresponding traditional frequency bands, but this is completely data-driven, so we didn't look for specific activity in these bands. It's completely data-driven, and you see that in the auditory cortex, we have this delta rhythm here, theta rhythm, alpha and beta, and very similar in the right auditory cortex. So this is the oscillatory makeup, if you want, of the primary auditory cortex. And this also means that it is quite well suited to process and analyze speech, because these are exactly the frequency bands that we would need to then entrain to these different timescales in speech. But I'm still skeptical, and this is at very best just indirect evidence. So this doesn't mean that these are actually rhythms that can entrain to the speech signal. Maybe theta. But yeah, so this is the spectral fingerprint of the primary auditory cortex. And now I would like to zoom in a little bit into this method and how it's possible to analyze spectral fingerprints. So you can do this with MEG or EEG resting state data, and it works quite well with both. You just need a few minutes of recording. So in the original study, we had 7-minute resting state data, but we have, in another study, we had only 5 minutes. That also works, but the longer the better, I would say. And especially with MEG, 7 minutes was quite borderline, because participants tend to fall asleep when they sit in a dark MEG chamber for a few minutes. So I guess 7 minutes is quite demanding already. And this is then an overview of the different steps that are necessary to analyze spectral fingerprints. And I just briefly zoom into this a little bit more so that you have an idea of what you would need to do. Okay, so first in sensor space, so either the electrode level or at the MEG channel level, a few steps are necessary. We segmented our 7 minutes continuous data into smaller segments. So we used 1 second segments here. If you have fewer minutes, then it might be necessary to use even shorter segments. But that meant we had about 420 trials or segments per participant. Then you can exclude some noisy segments. And then you would do a Fourier transformation for each segment to get a power spectra. We did this between 1 and 120 hertz, but of course all kinds, like every range is possible after 1 hertz, above 1 hertz in this case. And this looked something like this. So we had sometimes quite noisy power spectra for these 420 trials per channel and per participant. We then source projected our data, but you can also just stay on the channel level or on the electrode level. It's not necessary to go into source space. But yeah, source projection. Then quite importantly, we used spectral normalization, which means for every, in our case, voxel, we divided by the average power spectra across all trials and other voxels for one participant, which means we got rid of the 1/f power spectrum or 1/f activity. And then to reduce the data a little bit more, we used an atlas to be able to look into different brain areas without having like hundreds or thousands of brain voxels. So we used the AAL atlas, which is an anatomical atlas, and just averaged the power spectra for all voxels within one area. And then the crucial part is basically just clustering all these different segments that we then had. So we started out with these 420 power spectra for each participant and for each ROI. And this means for the AAL atlas, we had all these different regions of interest. So ROIs here. You can use a different atlas, a functional atlas, for example, or a more fine-grained atlas, and it would work just as well. And then we had two clustering parts. The first one was on the participant level. So all these 420 power spectra for every participant were reduced in their dimensionality by just condensing it down to 10 power spectra for each participant using k-means. this looked something like this. So if you imagine that these are the individual power spectra for the 1 second segments, then k-means basically tries to assign each of those individual power spectra to a cluster. So all the blue ones you see here, their shape is quite similar. So we used the k-means approach that looked at the shape of power spectra, so that if you had like a large alpha peak in a few of the power spectra, then these would get summed up or clustered into corresponding clusters. So all the blue ones are relatively similar in shape and are clustered into this blue cluster here, and the green ones are clustered into the green cluster here. So we had these 10 individual specific clusters per ROI. And then we also used Gaussian mixture modeling to create corresponding models. I have to say that these did not look very different from the k-means clusters. We just used this because Gaussian mixture modeling allows to compute the fit between the individual data and the cluster data, and we use these for different classification analyses. But you could stop here and just use k-means, and it would look almost identical. We then did the second clustering, which was on the group level. So we had our 10 individual power spectra per participant, and times the number of participants, which I think was 22 in our case. And this was then, again, using k-means, condensed to an optimal number of clusters per area. So for every area, we first checked what's the optimal solution for this. So does, like, for example, in the auditory cortex, does this consist of mainly 2 big rhythms, or are there more than 2? Are there 10 rhythms? So this number could be quite different. And for every region, we then had this optimal number of clusters that consisted of all these individual participant clusters. And again, used Gaussian mixture modeling, but just to do some statistical tests. And when you do that, you get spectral fingerprints. So here you see the spectral fingerprints for some other areas, not just the Herschel gyrus, and you see that they can look quite different. So for occipital areas, we very, very typically get 2 rhythms, 2 alpha rhythms, one with a slightly lower frequency and one with a slightly higher frequency, which matches with findings that in the occipital cortex we do actually have at least 2 distinct alpha generators. And then sometimes it's quite a mix. So here for the precentral gyrus, there were 5 distinct clusters, and we have alpha activity, beta, some delta, and theta, so it's quite a mix. For some of them, it looks very nice. For others, like the inferior frontal gyrus, we just have this delta activity and some like broad range gamma activity happening, and no other distinct peaks in between. And this is a way to basically describe the oscillatory makeup of different areas, or if you want, of just different channels in the EEG. You don't have to do source localization. So if you want to do this yourself, there are some relevant publications. For example, the original publication where we did this for the first time with the data and the script to do this on OSF. Then we also replicated this and compared it with a group of congenitally blind individuals to see how spectral fingerprints change in blind individuals. And there's a recent toolbox that came out, MATLAB-based toolbox that you can also use to calculate spectral fingerprints yourself. I have to admit that I haven't used this so far, but I think it's because it's very, very modular, and you can use different atlases, different kinds of data, and yeah, could be good. Okay. Next part, we have some questions now, because the next part is quite different, but we can also wait until the end to see how much time we have. So maybe if there are comprehension questions, that we can answer now. Yeah. 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 So it was trial and error, to be honest. We tried a different number of initial clusters, and 10 allowed us then to get the best results in the second level clustering. But it's a bit random. And in actually the new toolbox, what they implemented was that on the individual first level, they also used the optimal number of clusters for a participant and an between 2 and, I don't know, which is a good idea, but I haven't between this and an optimal number of clusters here. But yeah, it's pretty much random with some. Okay. Yeah. Just alpha frequency over time during rest, something like that, but not with this different rhythms. In the study here, they compare eyes open. You see alpha changes, not drastic changes. So the spectrums look pretty. Other things, like others, no aware that there's any studies that look at frequencies. What are you going to see? 5 participants, 22 participants here. 500 participants. The really general because that you see generalized across participants. It was also maybe a few more, but not that more. So really big sample where we can actually look at age, like yeah, that's to be continued.
I was wondering if the consider in a way influencing how you can estimate your work. There is a trade-off control for that. One to less representative.
Yeah, so you actually see the delta P over F, but it's just basically the way I interpret delta peaks is that probably there's something happening at even lower frequencies that we can't assess this. Yeah, but then we need to then be able to do the clustering. So there's really so we would need in the EEG or MEG, and then they fall asleep. So yeah, big way to do this, but lower frequencies.
There are some adaptive methods like
I think I have to try with this big sample. I think that's a good to play around. Okay, so for the last part, we'll go back to the king, so which is similar to the like stimulus response ideas we have heard in the first two talks. And just to like remind you what we currently think is happening, so brain activity to speech at these different scales, types. And there's a very, very clear findings that say the more speech, the stronger we track speech, we understand. But all of these studies basically suffer from some confound because these are usually parametric studies, so either they add different, like more and more noise levels, or they use noise for coding and make the speech less and less comprehensible. So they're outside the harder the condition, and then there's less comprehension. But we thought it would be really good to not alter the acoustics and to test whether more speech tracking is also associated with better comprehension if the acoustics are kept equal. For why we wanted to do this specific study is that speech tracking is extremely widespread in the So here you see results from a former colleague in Glasgow, Bruno Giordano. So put people in and played them some speech. This was clear speech. And then here he just shows speech tracking above chance in the brain. So source localized activity. He used mutual information, which we'll talk more about later. Method. And he looked at these different frequency ranges, and everything that is yellow or green or blue means that brain compared with a chance level. And you see that the whole brain is blue or green or yellow almost. So there's some areas like here or here that are gray, that are left out, but basically the whole brain tracks speech in all of these frequency bands. So we asked ourselves, is all of this tracking actually relevant for our comprehension? Because this was just passive listening here. And we thought the answer is probably no, because we already know that just because the brain tracks something, it doesn't mean that this also contributes to our perception or our comprehension. This next study, we also wanted to show that speech tracking predicts single track comprehension. And we had, again, MEG data, so we recorded MEG while participants were hearing sentences. The sentences were like the one you should have heard before, like, can you believe on Sunday night David examined 5 beautiful paintings? But this time they were embedded in noise. And yeah, I can't play this, but you would hear a male voice saying this with quite a high noise level on top. And we had a trial by. So after each sentence, participants had to say which adjective appeared in the sentence, and in this case, it would have been beautiful. And we determined the individual noise level, so the individual S&R ratio for every participant, so that everyone would get about 70% correct of the trials. And this worked somewhat. So our S&R, our like auditory staircase procedure wasn't perfect, but you see here the performance across for our participants, and they kind of cluster around the 70%. So every dot is an individual participant and the performance in this task, and they are between 58 and 80-something percent correct, which means for every individual participants, we do have some correct and some incorrect trials that we can actually contrast then. And so we used mutual information to assess speech tracking first above chance for these different frequency bands. And in this case, we didn't use generic frequency bands like delta, theta, or alpha, but we looked at the actual occurrence of words, syllables, phrases, and so on in our specific material, and then analyzed mutual information in these 4 frequency bands that represented the rate of these phrases, words, syllables, and phonemes. And this is the speech tracking analyzed with mutual information and source localized just above chance. And you see that at all of these frequent or timescales, frequency bands, we do have significant tracking. So this is, we've known this before, our brain tracks speech at these different timescales. But then we wanted to see what of this speech tracking actually predicts comprehension. And we contrasted correct with incorrect trials, and these are the results. And you see that it's quite different from the overall speech tracking results. And we basically showed that at the phrasal level, when participants tracked the phrasal level in the motor cortex quite well, then they could understand the speech. And the way we interpreted this is, we know that the motor cortex is really good at predicting the timing of upcoming stimuli. And because our stimuli were always structured in the same way, which I forgot to say, but every sentence had kind of the same components. And that means that it's relatively well possible to predict when the next phrase would start. And if you can do this well, if the motor cortex does this well, then it was also possible to better understand which adjective was being said. So we think this has to do with motor cortex and timing prediction. And the second effect we had was that in the temporal cortex here, this peaked in the mid-temporal gyrus, if the tracking at the word scale went well here, then participants could also understand the speech pattern. And this makes sense because, in particular, this area is known to map meanings to words. So if the segmentation into different words works really well, then it's easier for this area to map the meaning, and we can understand speech better. We didn't have any effects on the syllable or phoneme rate here. And this is just a summary of the results with these really, really nice brains that didn't come from us, unfortunately. But so in this study, we showed that only the tracking of words in the temporal cortex and of phrases in the motor cortex predicts single-track comprehension. But it's important to note that we showed this with this specific task, and there are probably task-specific effects. So if we had a task that asked participants to focus on the syllable level, maybe to look out for repeated syllables or something like that, then we might have had an effect at the syllable level. So yeah, this was this kind of finding and the study. And now I would like to zoom in into the second method that I wanted to introduce, which is mutual information. So mutual information, in general, measures how much knowing one signal helps us in knowing another signal. And this can also be expressed as the statistical dependence between two random variables. And it comes from information theory, so it's quite an old idea. But Robin Ince from the University of Glasgow has adapted this whole concept for neuroscience research. So exactly for the cases that are useful for us. And he has some nice illustrative examples on what MI can do, basically. So here you see just two variables and their association or their dependence, and in this case it's completely random, so there's no dependence between the two, it's just completely random variables. And in orange is the correlation coefficient, and in purple is mutual information. And because there's no dependence between the variables, both are 0. And then there are some examples of increasingly strong linear relationships. So here you can see that these get more and more dependent until the point where both variables are completely linear dependent, when you can see that the correlation coefficient is 1 and mutual information is 4. If we go into a negative dependency, we see that we have a negative correlation coefficient here, and mutual information doesn't care about the direction of any effect, so it's still 4. So we don't have a sign for mutual information. So far, so good. If you consider these cases, then mutual information doesn't add particularly much. It gets interesting when we look at nonlinear relationships. So here is an example where the correlation coefficient is 0, because with traditional linear methods, there's nothing we can find. As human observers, we see that this is not random. We see that there's this shape. And mutual information is able to detect this non-random relationship. And then there are some other examples where, again, in all of these cases, the correlation coefficient is 0, but mutual information, just like us as human observers, is able to find relationships. Except for this here, where every measure says there's nothing there, and we, maybe as humans, would say, maybe there's something there. But yeah, so mutual information is a very, very sensitive measure. If there's something in your data, mutual information will find it. If there's relationships between two variables, then mutual information will find it. And so what you need to compute mutual information, Robin has the MI toolbox on GitHub, so you would need that. And then you just need 2 continuous signals. In the case that I'm mostly interested in, you have like an external stimulus, for example, speech. It can also be music, or visual continuous stimuli, and on the other hand, a neural time series. So this can be source localized data, EEG channels, MEG channels, and so on. The speech envelope, I don't know how familiar people are with this here, but the speech envelope basically just quantifies the slow fluctuations in the speech waveform. There's a lot to say about that as well, how to compute that or what kind of assumptions we put into this, but it's easy to just think of it as slow fluctuations, the slow amplitude fluctuations in the signal. So a step-by-step guide of how you would do mutual information. So on the one hand, you need the speech envelope or music envelope, for example, that represents the slow amplitude fluctuations. We would then always bandpass filter this signal. In speech, usually people are interested in delta or theta, or are mostly interested in delta and theta. So that's how you would bandpass filter the speech. Then you do a Hilbert transform, which gives you a complex series of complex numbers. So you end up with the real and imaginary parts, which if you see it for the first time, it looks a bit funny, but yeah, you end up with these real and imaginary parts. I usually use both of these vectors, basically, to then compute mutual information. But from these complex numbers, what you can do is also just look at the phase or the amplitude of a signal, which is particularly useful if you are interested in phase relationships or phase amplitude relationships. Then it's good to have the phase of one signal and the amplitude of another signal. If you just use phase, then it's quite similar to phase coherence, for example. But I like to keep like the whole signal and just use like real and imaginary numbers for the analysis. And then quite important for mutual information is to normalize the data. And this is what where Robin basically, I think, put the most work in because he developed this Gaussian copular normalization. I almost don't know anything about that, but apparently it's very cool, and it's a binless approach, and it's particularly useful for neuroscience data. And then, of course, you need the other part, the other variable. And for speech-brain relationships, that would be the neurotime series, which can be electrodes, EEG electrodes, an MEG channel, or a voxel. You would then use the same bandpass filter, or if you're interested in phase amplitude relationships, you can filter one signal in, for example, theta and the other in gamma, and then look at phase amplitude relationships. But you would go through the same steps, and then in the end, calculate mutual information. So it's very short scripts. It's not long at all. It's not complicated at all. You just have to follow these steps, and then you get mutual information in bits. In theory, this measure makes results comparable across different paradigms, different studies. In reality, we do see quite a few differences in the strength of effects that we maybe wouldn't expect, so I would take that with a grain of salt here. Okay, so that's mutual information, and just another example of what this can look like, this time for EEG data and for music tracking. So for music, you can follow the exact same steps and also look at the music envelope. And here in this study, participants listened to tonal and atonal music, and this is the topography that we get with the mutual information values for every electrode. You see that there's this distinct topography that indicates that the effect is quite strong in this auditory blob here. But every electrode that has this white circle here means this is significant. So again, we have these widespread effects that almost the whole scalp shows significant tracking of the music envelope. So again, mutual information is super, super sensitive. And the relevant publications are here. First and foremost, Robbins' paper from 2016 that introduces this method, the specific mutual information method, and also his GitHub page that has these scripts. So it started with MATLAB. I'm using the MATLAB version, but I just saw that he also now has a Python version, Python scripts here. Then the results that I introduced, and so this is for auditory speech, but you can do similar things with visual speech as well. So here we looked at the opening and closing of the mouth and quantified this as a continuous signal, and then you can go through the exact same steps and also analyze mutual information between visual signals and the brain. Okay, to sum up everything, so we think that speech tracking is an important feature of comprehension, and it's necessary for us to actually understand what someone is saying. But the underlying mechanism is still unclear. So there are basically currently two camps, one call everything entrainment, and then the other camp that's a bit more careful. I belong to the second camp. But the auditory cortex does show a mix of intrinsic brain rhythms that is, in theory, quite well suited to track speech. And in this context, I introduced the spectral fingerprints. And some speech tracking mechanisms do predict single trial word comprehension. We had these two different effects, and in this context, I introduced mutual information. With that, I would like to thank you.
When the sentence is presented without any change in power, from before and after, then that might be good evidence of entrainment. Has anybody done
Not so much with before and during, but with during and after. So I think before and during, we wouldn't, if there was entrainment, yeah, we wouldn't expect, if it was entrainment, we would expect stronger phase coherence because the intrinsic oscillation gets aligned to the speech, but not so much a difference in the power. And if there's no, then maybe we would expect power differences. But I'm not aware that anyone has done that, like looking at before and during. I think that's, yeah, I don't think anyone has done that. What people have done is looking at after. Because with a new entrainment approach, you would expect that there's this ringing, so that after the stimulus stops, the oscillator would just continue for a little while to oscillate. So we would expect stronger power than compared with the non-intrinsic oscillations or non-entrainment approach, where we just think if it's all evoked, then if there's no external stimulus, then it just stops, and the power afterwards immediately goes down. People have done that more or less convincingly, not very convincingly for me. Yeah, and some studies show that it's a bit, that the power at the stimulation frequency continues to be slightly increased. But you always have methodological problems with this kind of approach, because as soon as you filter and look at power spectrum, then there's like washing out effects. So it's really difficult to just look at after the stimulation stops. So there are some methodological problems with this kind of approach, which is why I think probably many people have tried. But yeah, there are some publications that show similar things, but they all suffer from the same limitations, I think. Yeah, as I said, I don't think anyone has ever done that.
Because it's the idea that you have some intrinsic oscillation.
Yeah. Yeah, I mean, there's a recent study that I quite like that, but again, they look at not before so much, but during speech, listening to speech, where they quite convincingly show that, so that's from Joachim Groß again, where they quite convincingly show that for delta, you basically have strong delta when there's a landmark in speech, and then when there's no landmark, no onset of words, for example, then it just stops. And for theta, this is more continuous, like a continuous response. But yeah, the before and after is a bit tricky, and before could be worth a try, definitely.
So about your explanation about that the mode context is associated maybe with time phrases, why would it be specific phrases and not for example?
Because the phrases was the only thing in our stimulus material that was actually predictable. So everything else, like we had lots of different words, but basically the components, like last Sunday night, could have been yesterday morning. But so the words and the phonemes, everything is very different, but the rhythm of the phrases was always the same. Well, last Sunday morning, David examined could have been Sandra looked at. All these words can be very different, which means syllables and phonemes are different, but the phrasal components were relatively rhythmical and predictable.
Are there any other questions?
Did you also compare, say, the last part, the mutual information, like the information given by mutual information, and the simple correlation of the envelope and the I mean, do they get similar results?
Yeah.
Why use one and not the other? I mean, I understand fine mutual information is based on another theory, and but out there, most of the studies are using correlation.
Yeah, so in this field, phase coherence is the one that everyone uses. And for the music study that I did, I looked at the two. And the results are definitely qualitatively very similar. With mutual information, there are some other advantages that I didn't even mention here. You can, for example, put in several. You could put in several. Let's say if you're interested in audiovisual processing, you have the auditory envelope and visuals. Lip opening and closing envelope, something like that. You could put in several vectors, basically, that then you can compute mutual information for that, which other, like face coherence, for example, doesn't allow that. There's one other thing I wanted to say. Oh yeah, and another really cool thing with mutual information is also that you can compute basically it's like a partial correlation, but with mutual information, so you can compute out effects of different things. So it's a framework that allows you to be like widened out in many different directions methodologically. Yeah, so if you just look at a very simple case, then probably, for example, with the topography at the end with phase coherence, we would get smaller effects, so fewer electrodes that show a significant effect. But in the easiest case, that's probably everything. So qualitatively, if you have different conditions, then where you have more mutual information, you would also have more phase coherence, probably. But it just can be extended to these phase amplitude things that you can't do with other kinds of methods. So I think the flexibility is also something that I really like.
I have a question, because this sounds really great. And now I'm thinking, like, why are we not using this all the time? So, okay, maybe it's because it just hasn't caught on yet, but are there any salient disadvantages of mutual information?
Yeah, you need to continue signal, which you, like if you have different trials, like a paradigm that relies on trials, then you might not always have this. And you also need, so to really have robust results, you need quite a bit of information, quite a bit of a signal. So we usually have a few minutes of stimulation. You can do it with shorter trials, but the results definitely get less robust, and then you would need to use permutation approaches to kind of mitigate that. So I think the length. So this makes it really, really suitable, and it has caught on quite a bit with passive listening or passive watching of longer stimuli to really naturalistic situations. That's where it's really good at.
All right, cool.
Yeah.
Yeah, I got it. Thank you. Anyone else have a question? Yeah, go for it.
If I understood correctly, you use visual information for multivariate analysis instead of using bivariate, for example, each EEG signal with the target quality. Not
Yeah, so Joachim Groß again. They've recently started using this, and very cool results. And they also have scripts online, so you could try it yourself. But it's quite hard to understand, to be honest, what's actually happening there. But yeah, they have used that.
All right. Thank you very much.